In this example problem, we're looking at an object undergoing circular motion. In this case, we're going to consider a disk that is spinning around that has a small coin on it. A small coin means it's just effectively a small little point mass. So it just acts like a object at one spot right there. It's rotating around. This is kind of a top view, a side view. Looks like this. And we're trying to figure out how quickly it can spin, how many rotations per second, before the coin would slip off. Now, here's where we want to talk about why it would have to slip off. Well, the let's consider the forces on the coin. We'll do a free body diagram. There's going to be its own weight. The magnitude of that is m times g. It'll be downwards. To keep it from falling, there's a normal force perpendicular to the surface. It's always directly out of the surface that's applying it by the disk on the coin. And then there's a static frictional force, so long as it isn't sliding, that is pulling it in towards the center. Because, as we know, in order to maintain motion in a circle, it has to have a certain centripetal acceleration. Specifically, it has to have a component of the acceleration equal to v squared over r, where r is the speed of it. Or equivalently, you can write this as omega squared r, where omega is how many radians it is turning every single second. Now, the reason why this can be useful is because when I ask for a number of rotations per second, I'm talking about something called the frequency. And the frequency is the angular frequency, the angular velocity, how many radians it turns per second, divided by 2 pi, because every single rotation contains 2 pi 2 pi of radians of degrees. So you can rewrite this in terms of the frequency as the frequency squared times the radial distance away the object is, divided by 4 pi squared. Now, in order to have this acceleration, I need a component of the net force equal to the mass times the centripetal acceleration. In other words, the mass times the frequency squared times r over 4 pi squared. Now, if we look at this, the only force that's pointing inwards is the static friction. And that can be up to the coefficient of static friction times the normal force. Now, what this is telling us is that this can spin faster and faster, the higher and higher in frequency, with a larger and larger corresponding static friction, because this will equal to the net force. The net force in this case, the vertical will cancel, because there's no vertical acceleration. It's not falling down, for example, getting faster and faster down or up. But, so it's just the static friction that's supplying this. Excuse me, static friction. And so as the frequency goes up, the friction goes up until it reaches its maximum. So the maximum frequency is when we reach the maximum static force, which is equal to the coefficient of static friction times the normal force. Now, if we could consider the net force in the vertical, up and down, call that y, and this direction towards the center is centripetal. We have the normal force upwards. That's the vertical component of the normal force is the entirety, and so the entire magnitude is upward. And the y component of the gravitational force is the entire force, mg, but downward, so it's minus mg. And that'll equal to 0 because there's no acceleration in the vertical direction. And so the normal force is just mg. Note, if it was accelerated vertically, it would no longer equal to mg. So it's sort of coincidental that those things equal each other, and that's just because the acceleration in that direction is 0. But now I can use that, plugging in for the normal force. Now, if I solve for the maximum frequency, I have a few steps. First thing, this is squared, looks kind of like an L. As I divide by the mass, that would get rid of the mass on both sides. I would still have the static friction coefficient times g. I would have to multiply by 4 pi squared. I'd have to divide by r, and then I'd have to square root in that case. Now if I plug in my numbers, to see what that actually works out to, I get square root of 4 pi squared 0.4 for mu. The coefficient of static friction in the disk is 0.4. G, 9.8 meters per second squared, over R, which is 0.2 meters. And base SI units, 20 centimeters is 0.2 meters. If I plug that all in, I get 1.0 seconds. So it can spin up to 1 time per second before the coin would fly off. Per second. And the wrong units on here. Or per second is also known as hertz, by the way. So 1 hertz. And if you use like RPM for, say, an old vinyl player, those would correspond to, in those units, 60 RPM, because there's 60 seconds in a minute. So, kind of around the speed that a record player will play an old vinyl recording.